Hello. In this video, I'll present the gossip algorithm of Secure-Scuttlebutt, or SSB, a protocol that was designed for building social applications. Before delving into the main topic of the talk, let me first provide a tour of some applications that are built with SSB. Many of those applications are used for social networking, such as Patchwork on the desktop, and many mobile clients. SSB is also used by Peach Cloud, a Raspberry Pi-based self-hosting platform, and other specialized applications, such as GitSSB as an alternative to GitHub, and SSB Chess for correspondence display. There are many blocks in the technology stack of SSB, but we do not yet have a clear understanding of the full possibilities and limitations of the approach, both in theory and in practice. So as a first step in that direction, in this talk, I will present the SSB gossip algorithm from first principles, showing along the way a simpler variation for small and trusted groups. I will then briefly mention previous work that pioneered similar ideas. I'll finally conclude with currently open problems for future research. The core service that SSB provides is eventually consistent replication. This means that multiple users generating local events will eventually store all the events generated by other participants. Events are propagated through updates between random pairs of participants. And events propagate transitively between all participants, even if not all participants connect directly. The replication service is asynchronous, which means devices can be offline for arbitrarily long periods. It's authenticated, which means the authorship of events can be verified through an associated signature. It is secure, which means events are immutable for anyone but their author. And it's causal, which means that earlier events from the same author are received first. Moreover, the service does not depend on servers or internet connectivity, but can leverage both when available for faster propagation. We could equally say that SSB implements an asynchronous authenticated causal broadcast. Now, how is that implemented? The element of replication is an event with 5 fields. ID is the public key of its author to serve for identification, verifying signatures, and encrypting content. Previous is the hash of the previous event. Index is the position of the event in the log. Content is application specific, and signature is a cryptographic signature of the 4 other fields using the private key of the author. Events are chained in an append-only log, with each later event having a reference to an earlier event, or null in the case of the first. Because of the signature in each event, only the owner of the private key can append new events. And to enable efficient propagation of updates, as we'll explain right after, an implementation must ensure that logs are monotonic, which means that new information can only be added by appending new events, that it's linear, such that no 2 events have the same predecessor, that it's single writer, such that all log events have the same ID, which becomes the ID of the log, and connected such that all log events are transitively connected, then there's no gap in the sequence. Logs are then combined into stores, and the state of a store can be described by its frontier. The frontier is the pairs of log IDs and the highest index of events stored in each log. Logs in SSB publish events from multiple applications and data structure. Therefore, the frontier summarizes the state of all with a single number. Frontiers then enable efficient updates. So given 2 stores with different contents, each can send the other its own frontier. And then the difference between the 2 determines the events to be exchanged. After an update, both stores will contain the same events, making them consistent. And each store will only transmit the missing event from the other store, making update stores. Now, during updates, how should stores handle logs that they do not replicate yet? Well, in the paper, we propose a simpler model than what SSB does, which we call the open gossip model. And this model stores add the new log unconditionally. This model provides eventual total replication of events in all stores and total persistence of events in every store. We think this model can be sufficient for small teams with a high level of trust and is much simpler to implement and manage by users. However, it can be vulnerable to spammers and trolls because it does not provide agency to users in what they replicate. Therefore, to handle those problems, SSB instead implements Transitive-Interest Gossip, in which replication is determined by social signals that express interest in the content published by other authors. To receive new events from other authors, and authors start following them. And during an update, events will propagate from the original author to all others that are following them. A follow signal therefore represents a subscription to all past and future events of another author. A follow may not be reciprocal. In that case, new events will only flow in one direction. And replication is also transitively influenced by the interest signals of others. It is controlled by the number of hops for replication. With one hop, only participants directly followed are replicated. And with two hops, participants followed by a followee are also replicated. So this is the current SSB default, but each user can configure the option individually. In some cases, because of disagreements or non-overlapping interest, Eve, for example, may not be interested in Alice's content, even if she's interested in Bob's content and Bob is interested in Alice's content. For those cases, Eve can block other participants to prevent replication, even if she may be interested in two-hop replication in general. In practice, follow and block signals are implemented as events in participant logs and propagated in the same way as other events. They are then used to compute the set of followed and block IDs from the point of view of each participant. And these sets determine which logs are replicated in each update step. Social signals form a subjective social network for each participant with unique but most often overlapping interests, ensuring both individual agency while enabling global propagation. So this concludes the overview of the open and transitive interest gossip models. So many of the ideas I have presented so far have previously been proposed in many other papers. For example, Append-Only Logs are used in blockchains, Kappa architectures for replicated databases, and have also been suggested for accountability and providing secure timelines. The frontier-based replication of Append-Only Logs draws heavily from the design of a replicated key-value store that was used in Amazon DynamoDB. Using social signals for building replication overlay has been done also, and using social signals for spam and Sybil resistance was done in Sybil limit and reliable email. But even with abundant prior work for each individual idea, as far as we're aware of, SSB is the first synthesis of those to create a simple and elegant middleware for social application. To conclude, we presented an open and transitive interest gossip models based on Append-Only Logs that can be used as building blocks for distributed middlewares in which hardware and communication infrastructure is provided by participants themselves. The actual deployment and adoption of SSB with roughly 150 daily active users have shown the transitive interest model to be workable in practice. But there are still many open questions for research, such as with regard to efficiency, how can events propagate most efficiently through the network? And how can we bound memory usage in stores while retaining availability of data and simplicity of implementations? With regard to safety, how should replication deal with nonlinear, also known as forked logs, that may happen to be so intentionally or by mistake? And between the two, how can we implement efficient partial, yet verifiable replication of logs? And with regard to generality, what is the full range of distributed abstraction that can be built on top of SSB and similar protocols? And finally, with regard to privacy, how can participants control where their data flow? And what are the strongest guarantees that can be obtained? So with that, thank you for your attention, and you can find more detail in our paper.